much is this? Is x minus 1 I1 square over 2, right? Plus C. Right? Let's calculate the second part, this one. Let's calculate the second part. Yeah.
Is capital I equal to force?
No, sorry?
Oh, sorry. What's capital I?
No, just I break it down. Because I call this one, I wanted to calculate in one way. I call this one I.
Oh, okay.
I'm going to call this one 2I.
Oh, okay.
I'm not going to tell you about
Oh, okay.
how I told you about this thing before. We had an advanced course in Ohio State. It was called sliding mode control. This integral is a bit short. They are not very big. And you guys don't do it. This I think you don't do it. And we had a homework, and it was control. It was huge integration and this kind of thing. And so I used this abbreviation, to say, for example, I'm going to say A or I or something. Just instead of writing the whole integral, I put down. And go forward to finish the homework. One of my friends asked me, hey, can I have a copy of your homework? I didn't like it to give it to her, but sometimes you cannot. You ask. I give it to her. I told her be careful, change the thing. Do not copy exactly my homework because this is clear. If somebody copies it, this is very clear. But what she did, she called this one A for example, I put a 1 and 2, and she put, I don't know, A and B. But in the second page, she forgot. She put A and B, and I went through all my homework. I1 and I2 and go and all that. And after that, the professor called both of us for that one. And he knew, but what I did was not correct, But fortunately, he gave me the point because he didn't. I didn't say anything, but he knew what's happening. Just be careful. If you are copying, also be careful. My friend. Be careful with copying. I don't recommend that, but I'm saying if you are doing it, be careful. So I is that one. I is the first integral. Just I put the first integral here down. The second one.
Is it the same thing for the other one?
What?
For W, right?
No, for this one, I'm going to calculate it. See, because we had the lambda versus current, we said we are going to calculate the W prime. If it was the other way, it was the current versus lambda, I'll go calculate the W, right?
But are you going to call it like the I?
No, it's this one. I call this one I. I is not current, just number 1. I mean number 1. Number 2, this is not current. Number 1, this is the Greek. Number 1 term, number 2 term. Yeah, I can write everything. I can write it, completely. And it doesn't go for this. Right? Lambda 2 I di2. When the current is I1 is constant. I1. So let's come here. Let's put it here. So it's going to be integral of. So it's going to be x I1 3. But keep in mind, this one is a constant number. Keep in mind, that's a constant number. Plus I2 di. How much is the integral of this one? Is x I1 3 I2 plus C2, right? So how much is the W prime s? Is 1 plus 2, right? So we'll write it here. It's going to be x minus 1 times I1 squared over 2, forget the C1, plus x I1 3 I2 plus I2 2 over 2 plus C. This C is the C1 plus C. Just call it C, another constant. Right? Now how much is the force? How much is the derivation of this one? Is 1, right? Respect to x, right? Is 1. So basically it's going to be I1 squared over 2 plus, again this one the derivation is how much? 1. It's going to be I1 3 I2 plus plus what? How much is the derivation of this one? 0. How much of this one? So this is the, based on how much you currently have, you're going to generate this much, force in the system. I'm going to go one more example, and on the force calculation, I think I have to leave here. I may not have it anymore because I lost all my docs. I'm going to do the example. Okay, let's do this one. Another example here. We have a relay system like this. The material here, let's say the mu r is infinite. This is the ideal. The core is ideal. You have one air gap here, one air gap here, one air gap here. This one is the fixed part. This one is fixed. This one is the moving part. It can go up and down. Now, you have a winding here. The current is I. Number of turn is n. N is 600. The depth of this core, is 80 millimeter. We're going training today. We had a girl, she was from Ireland. The funny thing is, here in the US, we use British system, right? Pound, I don't know, inch, and those kind of things. But in Britain, in Ireland, they use the metric system. That's funny, in Britain, they use the metric system, but here in the US, we use the British system. So, 80 millimeter, this is by the way, metric system, 80 millimeter. This part is 80 millimeter. And here, let's see, this one is 16 millimeter. Here is again 8 millimeter. This is a G. Let's call this one, this gap is G. And the same thing here, this gap is G. And let me see how much is here. This is G. So it says if I is equal to if I is equal to 15 amps, if I'm correct, if I is equal to 15 amps DC, this current is the DC current. At what air gap, how much the air gap should be to have V equal to 1.4 Tesla? I think in the middle lane. I believe it's in the middle lane. In the middle lane, yes. This is a book problem. make sure it's the middle lane because
What is that?
hopefully in the middle lane. Let's calculate. So, and let's add one more part. I don't know, because it's kind of, yes.
Just clarify, the 80 millimeters, what does it represent?
Sorry?
The 80 millimeters is
The depth of this port.
Oh, okay.
Depth of this port. How?
8 meters?
No, 8 millimeters. So, if you want, we can take a little bit rest and continue the 620 or something. If anyone wants to leave, we can go forward. I'm going to go through 2 more examples on the magnetic circuit. If you can stay, let's go over non-stop. If you are tired, we can get a 10 minutes break and you can come back, whichever you guys want.
Go for it.
So, so, and let's calculate at this one. We want to calculate the general term for force. How much is the force? Because as soon as we have a current here, this one is going to absorb this one, right? Absorb this one. I can modify this part when we get to the solution of first part. I'll tell you more practice. So here I'm going to draw the magnetic circuit for this system. Should I worry about this part? Remember we said you go from here to here, here to here, here to here, here, from meter to here, all the meter, right? Should I worry about this part? Should I put the R for them? See, be careful in the exam. Sometimes you start to do something crazy calculation, which you don't need to do at all. I'm not going to put any resistance for the core. Because the core is ideal, right? The mu is infinity, right? So I don't care what the dimension of the core for those parts. So basically, there is a 1 resistor here, and 1 resistor here, and 1 here, right? 1, 1, and 1, right? And here also, so let's draw the circuit. I'm going to put one source here, NI, right? And see if we go this way, the flux is going up. Let's call it phi. Let's call it phi, right? So if the circuit was not ideal, I should put 1 resistor here. I'm going to put it here, but I'm going to get rid of them. 1 here and 1 here. 1 for the air gap, right? And 1 for this part, right? But this one I call it RC. This is 0 because the material is ideal, right? But I have I'll call this one RG1. I have 1 resistance here, right? I should have another one here, another one here, right? From here to here and here to here, right? But how much are those ones? 0. I'm putting the full circuit together. You can see the full circuit. But you don't have to put any values for those RCs, right? Because they are 0. I have 1 here, right? I call this one RG2. And this one is a RG2. Why I put the same value? Because the cross section is the same, right? And the length is the same, right? Reluctance is L over mu A, right? Both of them, they are mu 0. The A for both of them is the same. And the distance for both of them is same, right? So whatever is this one, is this one, right? So I should put another one here, right? Which is 0. Another one here, which is 0. Another one here, and another one here. Right? This is the full circuit. So the real circuit is going to be like the real circuit is this. I have one here, and I want to know how much this gap should be to have this much Tesla in the middle there, right? You know, RG2, what's the relation between RG2 and RG1? This one. What does it? Is it correct? Can you write it in the correct? Because the area here is double, right? The area here is double, right? And we say reluctance is L over mu A, right? If A is double here, right? This is 16 millimeter, this is 8 millimeter, right? If the area is double, so the reluctance is half, right? So basically, this is a RG2, and this one is a 1 over half of RG2, right? RG2 parallel with, I don't care about this one. If they would have told me 1.4 Tesla in this leg, I'm not going to simplify the circuit. But they say 1.4 Tesla in the middle leg, right? I do care only about this speed here, right? So RG2 parallel with RG2, how much is it? RG2 over 2, right? And I have another RG2, half RG2 here. Together it's going to be how much? RG2. So basically this one is going to be, see, when you simplify these things, be very careful, you know. This is very important to not lose this speed, you know. With all this kind of things I'm calculating, and still I'm calculating the right flux. This speed, see, is going to be the one is in the middle. If you simplify the circuit, suddenly you lose. For example, if you say there should be this much, right? You simplify here, calculate here. The phi you are calculating is not the one you're supposed to calculate. You know what I'm saying? In this equation, it says this one. I want to be here. So I'm going to calculate the phi in this way. So this circuit will be like this. Ni and simply RG. Right? 2 RG. So we want to know, and this is the flux. So flux is how much? RG, right? How much is the flux? BA after, right? How much is the A here? Nobody tells me. How much is the A here? 16 times 80, right? So A is equal to 16 millimeter times 80 millimeter. So phi is going to be minus 6. No, so this is the A times how much? How much will it be? 1.4. Right? And so we calculate it. So we calculate this thing. 1.28 times 1.4. Weber, or you can say 1.792 milliweber. Right? Now let's come back here. We're going to replace that one here. Be careful, you should replace Weber, not milliweber. So here it said 1.792 times 10 to the power of minus 3 should be equal to, how much is N? 600. How much is I? He said you want to see at 15 amps, how much